Welcome to the Clima podcast. In today's episode, I speak with Dr. John Straube. Dr. Straube holds a PhD in civil engineering and is a principal at RDH Building Science in Ontario, Canada, as well as being an associate professor at the University of Waterloo. In this discussion, John shares some of his pearls of wisdom after decades of experience, including building his own test structure at home during COVID. Clima inspires and educates people to create healthy, durable, and energy-efficient buildings to live, learn, work, and play in. Welcome today, John. It's really exciting to have you with me here on the Clima podcast.
It's great to be talking to someone on the other side of the world. I don't think we speak often enough, so I'm glad to be here.
Oh, fantastic. Do you get across to New Zealand much, John?
Not a lot. I think I can count on one hand. I think I've been 5 times in my life. And so most people would argue that's not often enough.
For sure. Now, John, if you can give us a little bit about your background and how you ended up in being one of the world's leading building scientists.
Well, how I ended up here, okay, we can talk about that. Whether or not I ended up as a leading building scientist, it means it's like maybe somebody you know. My real job is I'm a professor at the University of Waterloo, which is outside of Toronto, Canada. I'm split by time between the School of Architecture and the Civil Engineering Department. The other half of my time I spend as a consultant, and the company I've associated there is RDH Building Science. So how did I end up here? I was always interested in buildings. I recognized that I was more on the technical quantitative side, even in high school. Even though I wasn't very good at math, I had to work at that. And so the closest thing I could find was civil engineering. And after my first 3 years, I realized that actually civil engineering departments don't teach us much about buildings. They teach us a lot about structures and systems. And that's when I started looking at over the road at our School of Architecture and discovered that, by gad, those folks talked about buildings all day long and often deep into the night. But as I took courses in architecture, auditing them while I was doing my master's degree in civil engineering, I realized that there was no science at all being presented. Sometimes you'd get a little bit of what to build, even that was rare, but never why you would build it. And so that was where my graduate work, how I got started. I got eminently lucky that one of the few academics in Canada who were into building science, building performance, measuring outcomes was at my university. And so that I was able to do my graduate work with him, both my master's and my PhD. And I was just too stubborn to quit. And so here we are 25 years later. And I actually think that just hanging around in the industry for a long time and being focused just on building performance and energy and stuff means that you kind of pick stuff up. And so that's where I am now.
Fantastic. Now, can you give our audience a clear definition of what you would call building science and how and why is it so important in today's building industry?
Building science is something that's tossed around an awful lot in the English world. As you might know, in other parts of the world, like Japan, and certainly in continental Europe, they talk about building physics. And so we could talk about building science and how it is used by practitioners in those countries. But building science, in my world, it's sort of the science around performance of buildings. When you're that broad, you can include structure and acoustics and fire and moisture, and even today, energy and embodied carbon, because these are all things that you could quantify, that follow scientific rules, that can be managed by engineering processes. But building science and building physics, there is a reason to think about the distinction, is that the body of science that we apply might be better seen as the building physics. You know, the things that make energy and matter move and so on. But I think that one of the distinctions in North America about building science as a label is that it requires a much deeper connection to building technology and building practice than just building physics. And so much of what we talk about, write about, present about is that connection between, yes, heat flows from warm to cold and moisture from more to less, but how do I apply that in a world that we often build our buildings outdoor, I've discovered, even in New Zealand.
Yes.
And so the challenge with just studying building physics is you don't know that buildings get rained on, that there are surfaces that are dusty, that it's even amazing that they don't know that wood twists, because when you do lab tests, all the wood is perfect and square and all the rest of it. And so I think there's an awful lot of the practice of building science, and the way I apply to science in terms of academics is to know about those practical limitation, constraints, and realities, because just the physics of it is not enough. And I think that is actually an important distinction between many European building physics research and a lot of the North American building science research. When I think about what it means in New Zealand, I don't have a lot that I can base it on. I have obviously some interactions and court cases and et cetera. But it's kind of interesting that you use the building surveyor as somebody who is supposed to know about how buildings are built. And you have a distinct group of professionals who are supposed to know why it is built that way and how it should behave. That kind of disconnect I find quite problematic. It's actually quite important, more so in the building industry than many others, that we can connect how things work, but with how they're actually behaving in the field, how they're built, how they're operated, as distinct from the science of it, because we just can't control those things in the building industry like we might in other industries.
Exactly.
Simple question there, Simon. Ridiculously long answer, but it's because I think about this all the time.
Please feel free to go as long as you like, John. I really enjoy when you expand on your answers. Now, something that I've been thinking about a long time is we see many old buildings around the world that have been there for thousands of years compared to some of the buildings that we're building today, where within 10 years already, we've got huge issues. What do you think is the problem? What's going on here?
It's an important observation. You would be misplaced as a building science person to not ask that question. But I think it's also, there's a little bit much of rose-colored glasses. The first thing is, just at the very high level, the buildings we see today that are 100 years old are clearly the good ones, because the piece of junk buildings that were built in 1924 have long since rotted or been demolished because they were ineffective. That's sort of the first step. The second is that we don't have slave labor. So yes, I know that the pyramids are exceptional symbols of durability, but we can't build that way. And of course, we can build in other ways, but we have to make changes about both the materials, the labor, the life safety, et cetera, that we impose on today's buildings. Now, all that said, doesn't mean that there's no excuses here. We should be able to make our buildings not just last 100 years, but be better than they were 100 years ago. Because many of the buildings that were built 100 years ago aren't very comfortable, aren't very healthy, aren't airtight enough. And so I know some of them are, and we should be paying attention to that stuff, but lots of them aren't. We keep 100-year-old buildings around because they have physical durability and or historical significance. They may not be energy efficient. They may not be comfortable. They may not even be that perfectly fit for purpose. But to say that just because they last 100 years makes them better than what we build today is flawed logic. Is it true that some of those buildings 100 years old are better than some of the buildings we build today? Absolutely. That's a travesty, and we should be embarrassed. But we should also be noticing there are buildings we build today that are better in terms of durability, comfort, health, safety, and fitness for purpose than some of the buildings that were built 100 years ago. And we should celebrate that and learn from those successes.
That's great to hear. So, can you describe any benefits of hydrothermal modeling aside from ending up with a bit of a lighter wallet?
Well, if you think that a lighter wallet is beneficial, we should spend more time together, Simon. No, I actually think there's a tremendous amount of value that can be had out of hydrothermal modeling. But the value might be a little different than what people think. To me, the biggest value of hydrothermal modeling is as a tool for improving the user's understanding of the factors that influence hydrothermal performance. You can modify things in the model, cheaply and quickly see the effect of more rain, less sun, higher vapor permeability, more air leakage. This is, to my mind, not just a great training tool in the right hands, but even as myself, who's been doing modeling for almost 30 years, I'm scared to say. I was using Woofy when it was in Pascal and only German in 1996. I still use it to this day regularly to inform my understanding of what factors can and won't matter, do matter, how much they matter. The challenge is that people think that they get an answer from modeling that says, yep, this is a good design, or here's my design. Can you run a Woofy model on it and tell me that it works? That is not just wrong, it's often dangerous because people believe sophisticated computer models and don't understand the limitations. The garbage in, garbage out is never more true than it is with hydrothermal modeling. And so that's why if you really want to know an answer, you pretty much have to do a full-scale field test that's similar, calibrate your model, and then you can do quite confidently interpolation between examples that you've run, and with some caution, extrapolation. When you do that, it's astonishing how helpful and useful it is. The problem comes is that people use it as a shortcut to understanding both the physics and ignoring real performance. And so you have to bring in the reality and understand the physics when you're doing modeling, and then use it as an indicator, as a ranking tool, not as a predictor of this is going to work. I've just seen so much, as its use has expanded so much, I've just seen so much misuse. It's a little bit sad.
Yeah. So when it comes to the energy modeling, have we got a similar sort of problem going on?
In a way, it's worse, and in a way, it's better. The fact that your results can be wildly inaccurate has less of an impact on the building than when you actually get the enclosure modeling vastly wrong. But in terms of accuracy, it could be quite bad. And in fact, I think it's even more often wrong. But that's because in many markets, and I'm interested to hear that it is something happening in New Zealand, but in North America, increasing numbers of energy codes were asking for modeling if you go outside of standard prescriptive designs. And the problem here is that the design emphasis is, well, I just have to use it to comply with the code. Otherwise, I won't get a building consent. And so the strategy as a building owner is hire the least expensive energy modeler and give them the least possible time with the least possible information. And then tell them that you need the model so that you can get your building permit, your permission to build. Well, surprisingly, people try a lot of things in that short budget, short time to get it to pass. There's no incentive to be accurate. It's also almost always done as a post-mortem analysis. Most of the building design decisions have been made. You put it into a model, you pray to your favorite deity, and hopefully it passes. Hydrothermal modeling is more often used to try and tweak a design in the design development stage, et cetera, where it's much more appropriate. And in good energy modeling, again, has to be connected to some correlation with real measurements. So I have a good friend and colleague of mine who collected detailed, plug level data on 30, 40 buildings as part of a research project and used that to calibrate his modeling. So now he knows what's realistic and what isn't. But this person is not, you would never call this person and ask them to say, I need this model to prove code compliance, because that's not what they do. He does modeling to figure out what the actual likely performance is. And that's not what most energy models do. And that's a serious problem. That regulatory, I see this as not just an industry problem, it's more like a societal problem. Society is trying to reduce energy consumption and carbon emissions, but we don't have reliable tools and procedures to be able to meet that goal. And instead, we have a lot of people doing models and designs, and the outputs in terms of actual building performance are not correlated to what the energy model told us. I think that's a bigger problem than just, they're not a good model. I think it's a societal problem.
I really like how you talk so much about actually building something and doing tests and things. I'm actually working with one of my customers at the moment who's put about 100 different sensors into his building to measure temperatures, humidities, airflows, and all these things right throughout the different levels of the envelopes. So I was really interested when I watched your video the other day that you actually put together your own test rig at home during COVID.
Well, I've been inserting sensors in walls since 1991. Yes, I started when I was 4. And one of the things I've learned over time, having installed sensors in, I'm not exaggerating, over 100 buildings, including several in New Zealand, by the way, and often measured in the hundreds per building.
Oh, wow.
Is that sometimes the client expects that there'll be some sort of aha moment in the data, or that there'll be some sort of clear signal that suddenly the machine will go bing, and it means you have a fantastic product. And it's a little bit back to that hydrothermal modeling. It actually is so important that you become aware of how the thing actually works. And you then, every project going forward, you have in the back of your mind, how did that actually behave? What should I expect? And I'll give you something that's very simple. We can measure lots of complicated things. The easiest thing to measure is temperature. Once you measure the temperature in a real building, it becomes totally obvious how powerful the sun is.
Yes.
If you're facing north in New Zealand, the temperatures and the temperature variations that occur on a typical day is massive when you compare it to the south, and quite different than the east and the west. You can never think about wall performance again once you've seen that data about how variable it is. And then you work through things like moisture content and how much can it change in rate, humidity. Why does condensation happen and when, and how does that connect to the temperature? It's as much about training yourself in a way to think and to raise awareness about how things can behave as it is the exact data points, of which I have tens of millions. But that's not their value. The value is largely, I've come to believe, this understanding that you gain by watching a building and seeing the time scales and how things vary.
Quite amazing, isn't it? Now, was it you or Joe that coined the phrase the perfect wall?
That was certainly Joe Stiebrick. Absolutely. And the perfect wall's a kind of a cool story in terms of how it just took off. So the concept of the perfect wall, when we talk about the physical arrangement of layers, that was clearly understood and documented in the 60s by, at least I know, from the National Research Council of Canada, Division of Building Research. They actually went on the road and went to architects' offices and trade shows and wrote articles about why this is the better way. And everyone ignored them. Because, look, it was the 60s and 70s, and nobody really cared. The important thing about the perfect wall and Joe basically reintroducing the world to it was the timing was right. By that end of the 90s and the early 2000s, we were experiencing and being aware that we were experiencing significant problems throughout North America. There were, North Carolina and Vancouver and Newfoundland, and there was a whole bunch of specific failure rashes that involved hundreds to thousands of buildings. And people were aware that something wasn't working anymore. And so, as a way of trying to explain, if you're really serious about not getting into trouble, just do this, Joe came up with the concept of the perfect wall and made nice graphics that were understandable. And Joe he's an exceptional communicator and educator. And so it started to really make a difference. And so at that time, or shortly thereafter, Joe and I began to work together more formally. And so we were doing seminars together and et cetera. And so the two of us blabbermouths running around telling everybody who would listen that this was a way you started. It only took 20 years for it to start to make a difference. And it's literally 20 years ago that this all started. And now I actually have to kind of do a little bit of rehabilitation of explaining why the perfect wall should really be in quotes, because the perfect wall also has to include economics, available labor, available materials, environmental implications, for example. And also the perfect wall, I would say now the way I teach this is that the most important thing about the perfect wall is not the arrangements of layers. It is actually the labeling of the functional requirements. Every enclosure, whether it was built 100 years ago or today, needs an air control layer, a water control layer, a vapor control layer, a thermal control layer. It needs a support structure. And then often, optionally, it has exterior finishes and claddings. So the only difference between the 100-year-old wall and the wall today is what materials do I choose and have available for those layers? How well do the layers work? 4 inches of brick is not a good water control layer or air control layer or a thermal control layer. That's why those old 100-year-old buildings, we've knocked them down or we've renovated them. But that doesn't mean that 24 inches or let's say 60 centimeters of masonry isn't actually, hey, that's not a bad water control layer. That's pretty good for air if you got plaster on the inside. I'm thinking of, say, an old courthouse in Wellington that I attended for a while. And actually, thermally, people often go, oh, my goodness. Oh, they clutch their pearls at the lack of insulation. And it's like you realize that the thermal performance of that 60 centimeters of masonry vastly outstrips the performance of the best curtain wall installed in New Zealand today.
Wow.
So the conversation of design should start with those layers. Yes, the order that's shown in the perfect wall with the support on the inside, air, water, and vapor control outside of the support, and thermal outside of those membranes is ideal for the normal types of buildings in the normal types of climates using modern materials and labor. But there are many other ways to do a wall. And the reason I normally say is that, but they all require knowledge about the project and about science and about materials. And then we can start moving these layers around, mixing and matching, making some layers thicker and some thinner. And that is the art and practice of building science of enclosures. So the perfect wall, well, you don't need a building scientist. You just need lots of money.
Yeah. Now, I'm interested in you talking now about the naming of the layers. And how would you explain the difference between the term weather-resistive barrier and water-resistive barrier?
Oh, that's a really easy one. You've obviously been paying attention to some of my pet peeves. Weather-resistive barrier, I'm being a very simple person here. I would think it should be a barrier that resists weather. I include in weather the sun, the wind, the rain, the heat, the cold. That's all weather. So to me, I don't know that there is a layer, a product that does that. I think we call that the building enclosure. The reason we put all these layers together is so that it actually can be a barrier between the weather outside and the weather inside. So one of the things about a water resistive barrier, well, I think it also should be pretty clear on the surface. It should be a barrier to water. And the reason we add resistive to that is because most materials do not need to be and are not waterproof. So the WRB, water resistive barrier, has been in the US code since 2004. There was one hiccup. In 2003, they had a code that called it weather resistive barrier. And that was quickly beaten out of the code and fixed at the next revision. For some reason, 20 years later, people still call it a weather resistive barrier, even when they put requirements on not to be exposed for more than 30 days or 60 days or something. It's like mind-boggling that you can say weather resistive and not to be exposed in the same sentence. And they do. And this, by the way, is actually something I believe is underrated as to the importance. It's not the physics, but it's the language. And it's actually quite fun to work in New Zealand and see that you use different words for things like sarking,
Yes.
Which we would not use in North America. We'd use underlay or nogging or something like that. Okay, but actually, it's not that hard to get a dictionary to say this word means this thing. But we in the building enclosure business are so confused as a Tower of Babel about what is a water resistive barrier. Is a water resistive barrier an air barrier? I would say no, unless it's a water resistive and air barrier. Like crazy, man. Why don't we just label stuff in a clear and unambiguous manner? And I believe that there is a lot of, without control of the language, you do not understand. And if you don't see why it's such a big deal to call something a water resistive barrier rather than weather, or to call something an air barrier instead of water resistive, then you don't understand. So that's why it's so important to get that language right. I know short forms are convenient and often people understand, but this stuff's too important to say most of the contractors get it. We do need to be more careful and specific about our words. You know, you don't have to study a lot of physics. You need to know that an air barrier is different than a water resistive barrier. That's a pretty big deal. So I don't know if you'll let me go on riff on one other thing. You mentioned water resistive barrier.
You do that.
This is something that's quite unresolved. What is the difference between waterproofing, sarking, water resistive barrier, capillary break, or low slope roof membrane? So there are really important practical differences between those categories of products. The industry vaguely understands that if you're going to line a swimming pool, you're going to use a different product than you are going to use as a WRB behind a rainscreen cladding on a wood frame home.
Yeah.
But the manufacturer who sells that house wrap, WRB, will go to a trade show and show a standing column of 0.5 meter of water over top of that house wrap, letting people think that, oh, wow, that's a great waterproof system. Except it isn't. In real life, one of the things that we do differently between swimming pools and WRBs and houses is that we nail them to the wall. And then we nail furring strips and strapping over top of that. So the ability to withstand 0.5 meter of standing head is not just ridiculous on the face of it. Structurally, the wall would fail. It's that it has nothing to do with the product as installed. So when we install a low slope roof membrane, and I'm being quite careful not to call it flat roof because industry standards won't let us make it flat. You don't get warranty coverage. And that's because low slope roof membranes are not warranted for continuous exposure to standing water. And most people look at those membranes and they're going, well, that's waterproof. Not really. If you want waterproof, you have to move to something like Plaza Deck waterproofing or swimming pool liners. And that can be exposed to continuous water with a hydrostatic head. But this is why I'm saying something as critical to everyday practical building science as what is it waterproof or water resistant and what level of water resistance? Zero discussion. Zero discussion. Completely confused. All I know is that the salesperson tells me his product is fantastic. So I think summary, words matter.
Totally. Now, we're seeing obviously big increases in insulation values at the moment here in New Zealand. Can you explain to us a little bit about the importance of airtightness when it comes to insulation?
In Canada, this is simple because we have what we call winter. And that means it actually gets cold. I'm not talking, maybe Christchurch knows what I'm talking about here, but most of New Zealand doesn't. So when it gets cold, when you go skiing in Christchurch, you may wear a puffer jacket because you know it's going to be cold. Well, that's your insulation. If you go skiing with your puffer jacket unzipped, you're likely to freeze to death and be removed from the gene pool. So that's the difference between the importance of insulation and the importance of airtightness. And practically speaking, again, nothing is perfectly airtight, including your puffer jacket. Air's getting in underneath it and all the rest. And if you're just skiing and you're making lots of heat inside as a skier, it's okay that air gets in around your gloves and around your neck. If, on the other hand, you were to visit our Canadian North in the wintertime when it is minus 40 degrees and it's windy, you would learn that those oversights in air tightness will result in frostbite in a matter of 10 minutes. And so that's why, although the insulation level of a parka meant for minus 40 Canadian North is higher, the most important distinction is actually that it is more airtight. It controls the air leaks around your neck, around your waist, around your arms, all the holes. And so what we've seen over the years, and I'm looking back before my time in the 70s, when the first response to the oil crises came, we began with, of course, insulation. And as we added small amounts of insulation, people were not getting the benefit that they expected. And then they said, oh, we're going to have to plug up the holes. So they started plugging up the holes. They'd been plugging up holes in the past with building paper for the previous 50 years. But they added insulation, didn't get the full benefit. So then they started saying, oh, we should tape this, seal that, plug this. And it made a difference. And so then the next cycle was, oh, we should add some more insulation. So we added some more insulation. So we went from, say, 3 inches of fiberglass batting, and we went to 6 inches of fiberglass. Well, now we were, again, a little disappointed at the outcome. So we went through another round of air tightening. To be quite clear on this story, what actually tended to happen was that windows also played into the story. And we went through, my colleague Chris Schumacher calls the spiral of improvements, where it was go to better windows, do better insulation. Oh, now I have to improve the air tightness. Then we go better insulation, better windows. Now we improve the air tightness. So as we get to levels, say like a passive house, I don't know whether to call that extreme level or not, but it's often a very high level. Well, the only way that makes any possible sense is if it's matched with really good air tightness and really good windows. It's not a German philosophy. It's a fucking rule of physics that you need to be able to match those 3 components of typical houses to get the value out of each one of those components. So super airtight without good insulation, not good investment in money and time. Super good windows without air tightness, complete waste of money. And it's figuring out what we mean by sufficiently airtight for a particular insulation and window technology package. I think that changes with time. It changes with the technology and trades you have available, but you can't get too out of sync or you are misinvesting in resources. And airtightness seems to be the hardest one for consumers to conceptualize. In fact, they often misunderstand and completely don't understand that better airtightness can actually be directly connected to better indoor health. They assume because their experience was with bad buildings that better airtightness is connected to poorer air quality.
So going on from that, obviously we've talked about air quality. What about ventilation?
Fundamentally necessary in a modern building. It's fundamentally necessary in a modern airplane, in a modern train car, in a modern automobile, in a modern ship's cabin. So why people don't want to ventilate houses, again, I have systemic bias based on experience and knowledge. That means I can't understand or explain it. I know it exists. And it was actually part of our job to gain the trust of the public is to explain how important it is to have a known quantity and quality of air in any room that you or people you like are in. I mean, the quantity and the quality. And relying on mistakes by the Sparky and the plumber to provide air in your bedroom is just irrational. To hope that someone will get up in the middle of a winter night and open a window because you need air is just irrational. And increasingly in urbanized worlds, and Auckland is, I don't know what, half of New Zealand's population, urbanized areas, opening the window isn't even an assurance of good quality air. And so it's not just the consistent quantity, it's also making sure it doesn't have pollutants in it or pollen in it or the neighbor's cannabis smoke in it, whatever.
So we're seeing a lot of rainscreen design going on here at the moment. What sort of input can you put around rainscreens?
I suppose the first step is, what do you mean by rainscreen? Do you mean a ventilated and drained system?
What I'm talking about rain screens is where you're actually expecting some water to come through the cladding itself.
Well, that's interesting.
So, for example, a terracotta tile facade or something like that.
To most of the rest of the world, Simon, a rain screen only makes sense if you assume water gets through the cladding. I mean, that's what, screen and rain. So it's a thing that screens rain. It's not a rain stop or a rain barrier. It's a rain screen. So, well, of course, water gets through it. And then the question is, what do you do with that water? And draining it is the technical first step of dealing with the most water. Now, you don't need much of a cavity for that. It could be quite small. But if you have a larger cavity, the mistaken belief is that that means water won't get across the cavity. Except the bad news is that most of the water is getting through your cladding at penetrations like windows and details and decks and balconies. So the water is passing through the cladding exactly at the spot where it'll pass through the cavity. So, of course, water is going to get onto the other side of the cavity, which is why we put a water resistive barrier there. Key thing being water resistive. Because we expect water to get there, we must make it resistive. So rain screen design normally requires, I'm going to list them, 5 things. Nobody can see my one hand being held up here, but you need the cladding and it's got to be leaky. The easiest thing to buy is a rain screen cladding because if it doesn't already leak water, you can just drill a few holes in it and make it a rain screen cladding. So you have a rain screen cladding. Then I have a cavity that drains water. The water that passes through, I want gravity to take it down so that the water no longer moves sideways. That cavity could be a couple millimeters to 50 millimeters. Then I need a water resistive barrier, an underlayment, a sarking, a water repellent surface that is continuous. But that's not where it stops. Remember I said 5. I only told you the 3 things. But that now, the water running down, you have to direct it via flashing back out. And that means you need some holes, so weep holes. So those are your 5 components to make a rainscreen system at a minimum. But a lot of the world has moved well beyond the drained system that I described and calling rainscreen a ventilate, make the gap big enough that you can let air flow through it. And that means you don't need just weep holes at the bottom. You need vent holes at the top. And I know that that is not common in New Zealand for reasons that escape me, but it's been more than the direction. It is becoming the norm in most of North America for if you're going to do something called a rainscreen, you're going to open the top and the bottom, let some air move through to remove the droplets that don't drain. Is that sort of where you're headed? Because I think the word rainscreen is pretty critically important to let us understand again.
Well, certainly there's obviously the 2 differentiators, most definitely. And thank you for that really great description there, John. Now, we're sort of heading towards the end of our time. I thought it'd be really good if you could, just to summarize, give our audience some idea of where they can get hold of some of your resources. I know that you've written a book called High Performance Enclosures. Is that?
Well, yes. Couple of places I would start with. buildingscience.com. That is mostly Joe Stiebrick and Betsy Pettit's gift to the world. I've been lucky to be asked to write a bunch of stuff on that project, but that is one spot where you can really find a lot of stuff, particularly at the scale of New Zealand buildings. We're not talking 60-story high-rises there, and you're not doing that in New Zealand. Maybe you're a bit saner than that. There's also an attached bookstore, and at the bookstore, there's a number of good books you can get. And there's also my book on high-performance enclosures that you can get there, which is aimed at professionals who don't want to do a lot of calculations, but want to have understanding of the principles and some example drawings of how that might turn into a design for a wall or a roof or a connection. But RDH.com, that's the consulting firm I work with, RDH.com, also has a pretty burgeoning technical library and some of the things that might actually be more aligned to what New Zealand needs, in that there are a lot more about temperate rainforest type climates, a lot more examples about rainscreen furring and strapping and all the rest of it. So those would be good places. There's also buildingscienceeducation.net. Yep, that's one word, buildingscienceeducation.net, where there are free downloads which are targeted at people who are in the training industry, from trade schools into the university level, where there's just a more and more demand and need for clear and authoritative information about building science. So those would be sort of 3 websites. Can't tell you a TikTok channel. Too bad. Don't do that kind of stuff. But websites, I got lots.
Fantastic, John. Thank you so much for your time. And I will put the links to those in our description below.
It's been a blast, Simon.
Only a pleasure. Hopefully we can get you on again sometime soon. Sharing knowledge is at the heart of our strategy to make buildings better for everyone. Sign up for our podcasts to learn more about creating healthy living conditions by protecting building structures from external and internal moisture damage. Thanks for listening. Looking forward to having you with us next time.